live stream on this platform. Today I wanted to show the laser cutting audio about for you. Laser cutting use a first high power density line B to irradiate the workpiece, causing the irritated material to metal vaporized, abandoned, or reach the equilibrium point quickly, and at the same time use a high-speed airflow coaction with the beam to blow away the molten material, thereby cutting the workpiece. Laser cutting is one of the serial cutting methods. The principle of laser cutting is shown in the finger blow classification. Laser cutting can be divided into four categories: laser vaporization cutting, laser melting cutting, laser oxygen cutting, and laser scraping and controlled fracture. Laser vaporization cutting. The workpiece is heated by a high energy density laser beam, causing the temperature to rise rapidly, reaching the boiling point of the material in a very short time. And the material begins to vaporize to from vapor. The ejection speed of these vapors is very high, and at the same time as the vapor is ejected, and the incision is formed on the material. The vaporization heat of the material is generally very large, so laser vaporization cutting requires a lot of power and power density. Laser vaporization cutting is mostly used for cutting extremely thin metal materials and non-metallic materials such as paper, cloth, wood, plastic, and rubber, etc. Laser melting cutting. During laser melting cutting, laser heating is used to melt the metal material, and non-oxidizing gas is spilled through a loose caustic with the beam, and the liquid material is discharged by the strong pressure of the gas to form an incision. Laser melting cutting does not require the metal to be completely vaporized, and the energy required is only 1% of that vaporization cutting. Laser melting cutting is mainly used for cutting some materials that are not easy to oxidize or active materials such as stainless steel, aluminum, and its alloys. Laser cutting.
有买家进入直播间了。
Hello friends, welcome. The principle of laser cutting is similar to cutting. It uses laser as a preheating heat source and use active gas such as oxygen as cutting gas. On the one hand, the spilled gas reacts with the cutting melt to produce oxidation reaction and release a large amount of oxidation heat. On the other hand, the melt are blow cut off the reaction door to form a incision in the metal. Since the oxidation reaction during the cutting process generates a lot of heat, the energy required for this oxygen cutting is only 1% to of that for melting cutting, and the cutting speed is much greater than that of the laser vaporization cutting and melting cutting. Laser oxygen cutting is mainly used for easily oxidized metal materials such as carbon steel and heat-treated steels. Laser scraping and controlled fracture. Laser scraping use high energy density lights to scan the surface of bleeding materials, cause the materials to evaporate a small glue when heated, and then a certain pressure is applied, and the bleeding materials will crack around the small glues. The lasers used for laser scraping are generally switched lasers and lasers. Controlled fracture use the steep temperature distribution generated by laser gluing to generate local similar stress in the bleeding materials, cause the material to break around the small glue fixtures. Compared with other similar cutting methods, the overall characteristics of laser cutting are faster cutting speed and high quality. It can be summarized as follows. Good cutting quality. Turning to the small laser spot, high energy density of and faster cutting speed. Laser cutting can achieve better cutting quality. The laser cutting incision is narrow. The two sides of slit are parallel and perpendicular to the surface, and the dimensional accuracy of the cut parts can reach 0.05 millimeter. The cut surface is smooth and beautiful, and the surface roughness is only turns of big loss. Even laser cutting can be used as the last process without mechanical processing, and the parts can be used directly. After the material is laser cut, the width of the heat affected zone is very small, and the performance of the materials near the slit is almost unaffected, and the workpiece deformation is small, and the cutting accuracy is high. The geometric shape of the slit is good, and the cross-sectional shape of the slit presents a relative regular rectangular shape. The combination of laser cutting and Cutting method is shown in the table 1. The cutting in the table. The cutting materials is a 6.2 mm thick low carbon steel plate. High cutting efficiency due to transmission characteristics of the laser. The laser cutting machine is generally equipped with multi-sensing workbenches, and the entire cutting process can be fully sensor controlled. During operation, you only need to change the sensing program to apply the cutting of parts of different shapes, which can perform both two-dimensional cutting and three-dimensional cutting. Faster cutting speed. When cutting a 2 mm thick low carbon steel plate with a laser of 1020 volt, the cutting speed can reach 600 minutes. When cutting a 5 mm thick flower resin plates, the cutting speed can reach 1200 millimeters. The material does not need to be clamped and fixed during laser cutting, which can save both tuning and fixture and extra time for loading and unloading. Non-contact cutting. During laser cutting, the cutting charge does not contact the workpiece, and there is no way of the tool to process parts of different shapes. There is no need to replace the tool, only the output parameters of the laser need to be changed. The laser cutting process has low noise, low vibration, and low pollution. Many types of cutting materials. Compared with the plasma cutting, laser cutting materials are of many types, including metals, non-metals, metal-based and non-metal-based, composite materials, leather, wood, and fiber. However, for different materials, due to the physical properties and different absorption rate of laser, they show different laser cutting adaptabilities. Use the laser cutting performance of various materials is shown in the table 2. Disadvantages. Due to the limitation of laser power and equipment size, laser cutting can only cut medium and small thickness plates and pebbles, and the cutting speed decreases significantly as the thickness of the workpiece increase. Laser cutting equipment is expensive and requires a large one-time investment. Main features: nano cutting speeds and small deformation of workpiece. The laser beams is focused into a very small lattice board, so that the focus reaches a very high power density. At this time, the heat input by the beam far exceeds the part reflected, conducted or diffused by the material, and the material is quickly heated to the vaporization level, evaporating to form holes. Other than that, the beads and the materials move laterally relative to each other, so that the holes are continuous formed into a very narrow slit. The cutting edge is little affected by heat, and there is basically no deformation of the workpiece. During the cutting process, an action gas suitable for the materials being cutting is also added. When cutting steels, oxygen is used as an action gas to produce exochemical chemical reaction with the metal to oxidize the material and help blow away the slag in the slit. Compressed air is used to cut plastics such as foil, and internal gas is used to cut flame materials such as cotton and paper. The action gas entering the rosin can also cool the focusing lens to prevent the smoke and dust from entering the lens sheet to the contaminate of the lens and cause the lens to the overheat. Most organic and inorganic materials can be cut with laser. In the metal process industry, which occupies a large proportion of the industrial manufacturing system, many metal materials, regardless of their hardness, can be cut with deformation. Of course, for high reflectivity materials such as gold, silver, copper, and aluminum alloy, they are also good heat conductors. So laser cutting is different or even impossible. Laser cutting has low burns, wings, high precision, and is better than the plasma cutting. For many electronic manufacturing industry, modern laser cutting systems controlled by mere computer programs can easily cut workpieces of different shapes and sizes, so they are often performed over packaging and die processes. Although its processing speed is slower than die punches is it does not consume molds, does not need to repair molds, and the same time to replace molds, thereby saving process costs and reducing production costs. Therefore, is more cost-efficient overall. Non-contact processing. After focusing, the laser beam forms a very small action point with extremely strong energy. There are many characteristics of using it for cutting. First, the laser net energy is converted into amazing heat energy and maintained in a very small area, which can provide the narrow straight-edged cutting seams. The small is the heating affected zone adjustment to the cutting edge. Very small local deformation. Secondly, the laser beam does not exert any force on the workpiece. It is non-contact cutting tool, which means no chemical deformation of the workpiece, no tool wear, and there is no problem of tool conversion. The cutting materials does not need to consider its hardness. Thus, the laser cutting ability is not affected by the hardness of the material being cut. The materials of any hardness can be cut. Thirdly, the laser beam is highly controllable and has high adaptability and flexibility. Therefore, it is very convenient to combine with automation equipment, and is easy to realize the automation of the cutting process. Since there is no restriction on the cutting workpiece, the laser beam has unlimited contour cutting ability. Combined with a computer, the whole plate can be arranged to save materials. Adaptability and flexibility. Compared with other conventional processing methods, laser cutting has greater adaptability. First of all, compared with other similar cutting methods, similar cutting process, other methods can act on a very small area like the laser beams, resulting in wide incision, large heated affected zones, and obvious workpiece deformations. Lasers can cut non-metals, while other similar cutting methods cannot. Generally speaking, the quality of the laser cutting can be measured by the following 6 standards: cutting surface roughness, cutting slack size, cutting edge vertical and slope, cutting edge feed size, stripping training amount, flatness, application range. Most laser cutting machines are controlled by CNC programs or made into cutting robots. Laser cutting, a precision processing method, can cut almost materials, including two-dimensional or three-dimensional cutting of these metal plates. In the field of automobile manufacturing, cutting technology for space cars such as car top windows has been widely used. In the field of aerospace, laser cutting technology is mainly used for cutting special vacuum materials such as aluminum alloy, nickel alloy, stainless steel, composite materials, plastics, aerospace parts processed by laser cutting, including energy flame tubes, aircraft flames, window gratings, tailwinds panels, helicopter main rotors, space shaft, ceramic insulation titles. Laser cutting forms technology is also widely used in the field of non-metallic materials. It can not only cut hard and brittle materials such as silicon nitride, but also cut the processing flexible materials such as cloth, paper, plastic plates, rubber. For example, use laser tool cutting cloth can save 10% to 12% of clothing materials and improve efficiency by more than 3 times. The materials will get better results when cut with oxygen when oxygen is used as the processing gas. The cutting edge will be slightly oxidized. For plates up to 4 mm thick, high pressure cutting can be performed with liquid as the processing gas. In this case, the cut edge will not be oxidized. For plates with a thickness of more than 10 mm, use special plates for the laser and applying oil to the workpiece surface during process can get better results. Despite its high reflection and semi-conductive aluminum material with a thickness of less than 6 mm can be cut. Depending on the alloy types and the laser capabilities, when cutting with oxygen, the cutting surface is rough and hard type. When using the cutting surface is smooth. Both materials have high reflection and very good similar conductive. Okay, that's all the knowledge I wanted to show you. The next time, my colleague Lydia will show some knowledges. Thank you.
Hello everyone, welcome to our broadcast room. I'm Lee from Novo. We specialize in low volume manufacturing and other process. Next, I will introduce the 3D printing to you. First, 3D printing or additive manufacturing is a process of making three-dimensional objects from a digital file. The creation of a 3D printed object is achieved using additive processes. In an additive process, an object is created by laying down successive layers of material until the object is created. Each of these layers can be seen as the thinly sliced cross section of the object. There is one exception, though, and it's called volumetric 3D printing. With volumetric printing, entire structures can be formed at once without the need for layer-by-layer fabrication. It's worth nothing, however, that as of now, volumetric technology is primarily in the research phase. 3D printing is the opposite of subtractive manufacturing, which is cutting out, hollowing out a block of material with, for instance, a milling machine. 3D printing enables you to produce complex chips using less material than traditional manufacturing methods. And how does 3D printing work? It all starts with a 3D model. You can opt to create one from the ground up or download it from a 3D library. 3D software. There are many different software tools available. We have created an overview on our 3D software page. We often recommend beginners to start with ThinkCard. It's free and works in your browser. You don't have to install it on your computer. ThinkCard offers beginner license and has a built-in feature to export your model as the printable file. Now that you have a printable file, the next step is to prepare it for your 3D printer. This is called slicing. Slicing from file to 3D printer. Slicing basically means slicing up a 3D model into hundreds or thousands of layers and is done with slicing software. When your file is sliced, it's ready for your 3D printer. Feeding the file to your printer can be done via USB, SD, or Wi-Fi. Your sliced file is now ready to be 3D printed layer by layer. 3D printing industry. Adoption of 3D printing need to transform almost a major industry. Examples of 3D printing. 3D printing encompasses many forms of technologies and materials as 3D printing is being used in almost all industries you could think of. It's important to see it as a cluster of diverse industries with myriad of different applications. A few examples: consumer products, eyewear, footwear design, furniture, industrial products, manufacturing tools, prototypes, functional end-use parts, dental products, prosthetics, architectural scale models, maquettes, reconstructing forces, replicating ancient artifacts, reconstructing evidence in forensic pathology, movie props, rapid prototyping, rapid manufacturing. Companies have used 3D printers in their
有
design.
买家进入直播间了。
Hello, welcome to broadcast room. What process do you want to know? we introduce the 3D printing. Companies have used the 3D printers in their design process to create prototypes since the late 70s. Using 3D printers for this purpose is called rapid prototyping. Why use 3D printers for rapid prototyping? In short, it's fast and relatively cheap. From idea to 3D model to holding a prototype in your hands is a matter of days instead of weeks. Iteration are easier and cheaper to make, and you don't need expensive molds or tools. Besides rapid prototyping, 3D printing is also used for rapid manufacturing. Rapid manufacturing is a new method of manufacturing where business use 3D printers for short-run, small batch customer manufacturing. Automotive car manufacturers have been utilizing 3D printing for a long time. Automotive companies are printing spare parts, tools, and fixtures, but also end-use parts. 3D printing has enabled on-demand manufacturing, which has led to lower stock levels and has shortened design and production cycles. Automotive enthusiasts all over the world are using 3D printed parts to restore old cars. One such example is when Australian engineers printed parts to bring a taxi back to life. In doing so, they had to print parts that were out of production for decades. Aviation. Aviation loves addictive manufacturing, largely due to the promise of lightweight and stronger structures offered by 3D printing. We have seen a whole bunch of innovations in the domain of aviation lately. With the appearance of the next printed atom was never destined to be fitted to an aircraft, but, but rather it was designed to be installed in a facility for testing flow conductions at hypersonic speeds. When flying in the hypersonic flight region above, the air passing around the vehicle becomes incredibly hot and the pressure increases significantly. These conductions can cause the air itself to become chemically reactive, which causes issues for fuel-burning vehicles. Setting flow conductions with computational flow diagnostics is computational expensive, and so to replicate the flow conduction, researchers at Purdue fabricated a giant burner to recreate the hot, fast, high-pressure experienced in hypersonic flight. In short, they basically built a rocket nose and they placed the test components in the exhaust plume to see how they performed. Types of 3D printers. The three most established types of 3D printers for plastic parts are stereolithography, SLS, and FDM. Formlabs offers two professional 3D printing technologies, SLA and SLS, bringing these powerful and accessible industrial fabrication tools into the creative hands of professionals around the world. Stereolithography. SLA was the world's first 3D printing technology, invented in the 1980s, and is still one of the most popular technologies for professionals. SLA 3D printers use a laser to cure liquid, resin into hardened plastic in a process called Photolithization. SLA resin 3D printers have become vastly popular for their ability to produce high accuracy, isotropic, and watertight prototypes and parts in the range of advanced materials with fine features and smooth surface finish. SLA resin formulations offer a wide range of optical, mechanical, and thermal properties to match those of standard engineering and industrial thermoplastics. Resin 3D printing a great option for highly detailed prototypes requiring tight tolerances and smooth surfaces, such as molds, patterns, and functional parts. SLA 3D printers are widely used in a range of industries from engineering and product design to manufacturing, design, jewelry, model making, and in education. Is ideal for rapid prototyping, functional prototyping, concept molding, short-run production, dental applications, drawing, prototyping, and casting. SLS 3D printers use high-power laser to sinter small particles of polymer powder into a solid structure. The unfused powder supports the part during printing and eliminates the need for dedicated support structures. This makes SLS ideal for complex geometries, including interior features, undercuts, thin walls, and negative features. Parts produced with SLS printing have excellent mechanical characteristics, with strengths resembling that of injection molded parts. The most common material for selective laser sintering is nylon, a popular engineering thermoplastic with excellent mechanical properties. Nylon is lightweight, strong, and flexible, as well as stable against impact, chemicals, heat, UV light, water, and dirt. The combination of low-cost parts, high productivity, and established materials make SLS a popular choice among engineers for functional prototyping and a cost-effective alternative to injection molding for limited run or bridge manufacturing. SLS is ideal for functional prototyping, end-use parts, short-run bridge, or custom manufacturing. FDM, also known as fused filament fabrication, is the most widely used type of 3D printing at the consumer level. FDM 3D printers work by extruding thermoplastic filaments such as ABS, PLA through a heated nozzle, melting in the material and applying the plastic layer by layer to a build platform. Each layer is laid down once at a time until the part is complete. FDM 3D printers are well suited for basic proof of concept models, as well as quick and low-cost prototyping of simple parts, such as parts that might typically be machined. However, FDM has the lowest resolution and accuracy when compared to SLA or SLS, and is not the best option for printing complex designs or parts with intricate features. Higher quality finishes may be obtained through chemical and mechanical polishing process. Industrial FDM 3D printers use soluble engineering thermoplastics, but they at a steep price. FDM is ideal for basic proof of concept models, simple prototyping. Application areas of 3D printing. The first one is manufacturing and industrial application. 3D printing technology is used in the manufacturing industry mainly for prototyping, rapid manufacturing, and low-volume production. It can manufacture complex parts, molds, and tools such as engine parts and seat brackets, thus reducing manufacturing costs and improving productivity. Medical field. 3D printing technology has great potential in the medical field. It can be used to create personalized medical devices, implants, prosthetics, and artificial limbs customized to the patient's body structure to provide better fit and comfort. In addition, 3D printing can be used for bioprinting, such as research in tissue engineering or organ transplantation. Aerospace 3D printing technology is used in the aerospace sector to manufacture complex parts, lightweight structures, and engine components. It can improve the performance of aerospace equipment and reduce the weight of components. Automotive industry 3D printing technology is primarily used by automakers to create prototypes, customize parts, and production tooling such as dashboard panels and door handles. This helps speed up vehicle development cycles, reduce costs, and increase productivity. Construction 3D printing technology is used in the construction sector to print building structures and components such as precast concrete wall panels and building exterior finish. This can reduce construction costs, speed up construction, and enable more complex and innovative designs. Consumer goods 3D printing technology can be used to create personalized consumer goods such as customized shoes, eyewear, jewelry, and home furnishing. Education and research 3D printing technology is widely used in education and research to create instructional models, experimental devices, and scientific prototypes. Art and culture. Artists and designers use 3D printing technology to create artworks, sculptures, and installations. This technology offers new ways to express creativity and uniqueness. Food industry 3D printing technology is used in the food sector to create special shapes and the structure of food such as chocolates, candies, and pastries. Energy and environmental protection. 3D printing technology can be used to create components for energy devices such as solar panel mounts. In addition, waste plastics can be transformed into reusable products by 3D printing technology, reducing waste generation. The benefits of 3D printing as an additive manufacturing process, building objects by adding material layer by layer. They offer a unique set of advantages over traditional subtractive and formative manufacturing process. Speed. With traditional manufacturing process, it can take weeks or months to receive a part. 3D printing turns 3D models into physical parts within a few hours, producing parts and assemblies from one of concept models to functional prototypes and even small production runs for testing. This allows designers and engineers to develop ideas faster and help companies to bring products more quickly to the market. Engineers at the turned to 3D printing to rapidly produce 500 high-precision drilling cuts used in drilling drills for Airbus, cutting the lead time from weeks to only 3 days. Cost. With 3D printing, there is no need for the costly tooling and setup associated with injection molding or machining. The same equipment can be used from prototyping to production to create parts with different geometries. As 3D printing becomes increasingly capable of producing functional end-use parts, it can complement or replace traditional manufacturing methods for a growing range of applications in low to mid volumes. Customization from shoes to clothes and vehicles. We are surrounded by products made in limited, uniform size as business strive to standardize products to make them economical to manufacture. With 3D printing, only the digital design needs to be changed to tailor each product to the customer without additional tooling costs. This transformation first started to gain the foothold in industries where customer fit is essential, such as medicine and dentistry. But as 3D printing becomes more affordable, it's increasingly being used to mass customize consumer products. Design freedom. 3D printing can create complex shapes and parts, such as overhangs, microchannels, and organic shapes that would be costly or even impossible to producing with traditional manufacturing methods. This provides the opportunity to consolidate assemblies into less individual parts to reduce weight, alleviate weak joints, and cut down on assembly time. Unleashing new possibilities for design and engineering. Nervous System launched the first ever 3D printed ceramic jewelry line consisting of intricate designs that would be possible to manufacture using any other ceramic technique. Reduced risk. Product development is an interactive process that requires multiple rounds of testing, evaluation, and refinement. Finding and fixing design flaws early can help companies avoid costly revisions and tooling changes down the road. With 3D printing, engineers can thoroughly test prototypes that look and perform like final products, reducing the risks of usability and manufacturability issues before moving into production. The developers what are the primary advantages of 3D printing? 3D printing is an additive manufacturing. Hello, welcome to our broadcast room. What process do you want to know? Now we are introducing the 3D printing. Do you want to know the 3D printing advantages? 3D printing is an additive manufacturing process where the three-dimensional object is crafted layer by layer, following the digital model. 3D printing manufacturing technologies have undergone immense advancements. No longer confined to prototyping or simple designs. Modern 3D printers can produce complex geometries, employ a range of materials from plastics to metals, and are utilized in industries ranging from fashion to aerospace. Before we dive deep into the plethora of advantages, let's skim the surface and grasp the broader benefits of 3D printing as an additive manufacturing technology. For most rapid prototyping and fast design, the beauty of 3D printing lies in its transformative capability. When a company has an idea, 3D printing can swiftly convert this idea into a tangible prototype, unlike traditional manufacturing methods that often involve extensive tooling and setup. 3D printers can produce a part as soon as the design is finalized. This speed is revolutionary in product development. Consider the following: immediate realization of concepts. As soon as designers have a 3D model or CD file, they can use the 3D printer to bring that design to life. It eliminates the prolonged waiting time of other manufacturing process, real-world testing, and after printing and post-processing. This part is ready for testing, and the designers can adjust the model to incorporate any needed modifications and print again, allowing for rapid iteration based on real-world feedback. Customization on demand. In the same way, if a customer or client wants a slight tweak to a design, it can be done very quickly without alerting the entire manufacturing process. This approach speeds up product development and paves the way for innovations and ideas to come to life in record time. Cost effective. While the initial investment in 3D printing equipment might be substantial, the long-term benefits and the return on investment are profound. Additive manufacturing, the underlying principle of 3D printing, is a game changer in cost management. Here's why: savings on material costs. The 3D printing process only adds materials where needed. This method contrasts sharply with processes like CNC machining, injection molding, or other manufacturing technologies, which remove material leading to potential waste. As such, there can be a marked reduction in material costs with 3D printing. Labor and operational efficiency. A traditional manufacturing process often requires skilled labor for various tasks, from operating machines to post-process. Okay, our introduction is now to end. Welcome to inquiry our product.